All right, guys, so we're going to start topic 8 in this video, and it's a pretty long and intense topic, so I'm guessing this is probably going to be about 2 to 3 parts depending. So we'll kind of see how long I can go on before we take a break here, okay? So we're going to start talking about stress transformation, and there are a couple of different ways that we can calculate and understand stress transformation, but primarily we're going to be focusing on a method called Moore's circle, or using Moore's circle to solve for stress transformations. So I'll show you a couple of different ways, but we're going to just kind of use a later method that I show you that takes up most of this topic, okay? So before we get into some problems, we have a couple of slides on, or more than a couple slides on kind of backstory or theory, what's going on here. So let's talk about first, what is plane stress transformation? So if we remember, when we first started talking about stress and we started talking about this class, we talked about how we could have stress for 3D elements, which is what we kind of see in the real world, or how we can kind of characterize those as 2D elements. But we do remember that if we did want to characterize, the 3D state of stress, that we could kind of talk about stress in terms of these 6 independent normal and shear stress components, okay? And these act on all the faces of the elements. So in engineering practice, we don't generally use this state of stress, but instead what we do is we figure out these ways to kind of approximate and simplify the loading so that we can analyze the stress of an element using just a single plane. So we don't have to use all of those planes and all of that kind of complexity of each element, but we can just look at a single plane. And when we're looking at this one plane, we call this just plane stress because it's just acting on that one 2D surface instead of kind of the entire thing. So here is this general state of stress. We have these stress values acting at all of these planes, and then this is what plane stress does, is it simplifies this to say, okay, well, we don't need to consider all of the stresses acting on each plane. We can consider just the shear and the normal stress in each of these directions, and this is an approximation, it's a simplification, but it should be enough. Okay, so the general state of now plane stress. So we're looking at this 2D element here. And we can represent this basically by a combination of 3 stresses. So we have 2 normal stresses, one in the x and one in the y direction. And then we have a shear stress that we just kind of say is tau xy because it's acting in that vertical direction. So it's a shear stress instead of that normal force which is coming out of your element. And these stresses act on the 4 faces of this element. So you can kind of refer to this 3D model if you need to understand more about how that works, but we can kind of just isolate this 2D element and make things look a little bit easier. So the idea here is we're going to use the XY axis for all of our stress transformations, but what happens is a lot of times we need to know what the stress is on inclined plane. So not necessarily on purely the X or Y axis that we define, which would be like this, but we need to rotate these axes to look something maybe like this. And we call these rotated axes our X prime and our Y prime axes. And you can see that's what's happening in this element here. All we're doing is we're taking that block and we're rotating it by some theta. But then when we do that, what happens is all of these stress components, they're vectors. So now their magnitude has changed, just like their direction has. Okay, so what now happens here is that we can no longer say, well, that this is defined by sigma x, sigma y, and tau xy, but now the minute I rotate by some theta, I'm going to say that they're defined by some sigma x prime, sigma y prime, and tau x prime y prime, which means the sigma, the normal stress in the x prime direction, the normal stress in the y prime direction, and the shear stress in the x prime y prime direction. Okay, and we'll go over kind of a method to solve for this using equilibrium, which is not my favorite method because it requires a lot of keeping track of your vectors, which gets really difficult with all of these stresses everywhere. And then we'll go over another method, which is Moore's circle, which is much easier once you kind of get the hang of it. Okay, So just to reiterate what's happening here, the state of plane stress is always defined by these three components. So these two normal and one shear. And we're going to use these throughout this entire topic. And these three components are different the minute I rotate that element. So the minute I apply some theta, the minute theta is not 0, then I can no longer just say that these are those, that sigma x, sigma y, and tau xy are the same for every theta. It's a function of theta, so they're changing. So I would have to recalculate those. Okay, so now the question is, well, it's pretty simple to get what those three stresses are for an unrotated element, but how do I calculate them for a rotated element? So transforming them from the non-rotated to the rotated element is really similar to the way we do vector analysis to combine forces in different directions. So really, you don't need anything else besides statics to be able to do this. You just have to remember how to combine things using magnitude and directions, your sines and cosines. The only difference is you have to really keep track and organize your work because we have to account for magnitude and direction of each stress component and then the area that that acts upon, because don't forget, let me just come back here. This is the 2D plane, but really it's of an entire stress block that looks like this. So you're representing a plane, but it's an entire stress block. So we have to multiply that stress by the area in order to do this vector analysis. Okay, here is the complete procedure for this analysis. I'm going to go over one example on how to do this using the equilibrium way, and then after that we're going to only focus on Morse circle because I think that you'll see how much simpler of an application that is. And also in your suggested problems, I didn't give you any problems where you'd have to do this using the equilibrium way, so the way that's kind of mentioned here. This is just so you understand that like this is also an option for you to try and to do. But Morse circle is much simpler, and especially when you start getting into more complex problems, it's a much easier method to use. Okay, so here's the one example that we're going to do. Let's read through it. So the state of plane stress at a point on the surface of the airplane fuselage is represented on the element oriented as shown, and represent the state of stress at the point on an element that is oriented 30 degrees clockwise from the position shown. So what we're going to do here, and just for reference, I believe this tells you everything about which direction we're going to be, which direction is positive, which direction is negative. So you can use this for reference, but you can also define your own positive and negatives. Okay, so what we're going to do here is this element is already sectioned off for us. So I'm going to first draw this rotated element, what's happening here. Basically, this element is going from this to a rotation of 30 degrees that looks like this. And we have this AA cut and this BB cut. So we want to obtain the stress components, and we need to first section the element by that cut AA. So I'm going to put here to obtain a rotated element we need to make a cut at section AA. So I'm going to do that down here. I'm going to come here, I'm going to draw whatever is left of that. This would be AA from here to kind of here. And what we have here is we have some delta A. This is the area. The bottom segment's removed, so this inclined plane has an area of delta A. Okay, this is a 30-degree rotation of the element. That means that this would be delta A cosine 30, delta A sine 30. And what we want to do here is we want to draw our free body diagram of this element. So I'm going to kind of redraw this triangle, maybe a little bit bigger because we have all these stress components. And then let me first define the axes that we have. So here, we're going to start by defining the x prime axis as the one that we just rotated. So we're going to define our x prime axis through here. Okay, and we're going to define our y prime perpendicular to that through here. And so just to be clear what's happening, this is our x prime. These should look perpendicular, they kind of don't. And what we did was we rotated this this 30 degrees. And this was our original x-axis was right here. Okay. So just to come back here, 30 degrees clockwise. Okay. So if it was 30 degrees clockwise, that means measuring counterclockwise, then this would be 60 degrees, just so we're all clear about what's happening. Okay. Now, if that's the case, let's draw our all of our shear and normal forces. So let's start with the normal forces. We would have a normal force coming out in this direction. We would have some force coming out this direction, something coming out in this direction, and then we would also have our shear acting along these planes parallel. Okay, and what we know about these is we know that our shear here is going to be tau, this is x prime, y prime, times delta A. We know here we have this 25. Here we would have 25 delta A sine 30. And then we would have our normal forces of 80 delta A sine 30. This is an x prime now. And then our normal here, which would be the 50 delta A cos 30. So what I'm doing is I'm just taking everything from here and rotating it that 30 degrees and now putting it in components. So you see the 25 doesn't change just because I already had that, that same shear stress on the bottom right there. Okay, so now what we're going to do is we're going to use equilibrium to solve for this. And you can see how messy this already looks, but let's start. Okay, so we're going to sum our forces in the x prime direction, and we're going to set everything equal to 0 here. And we're going to say that's the positive direction. And all we have to do is kind of compile everything that's going in that x prime direction. So we have the sigma x prime delta A minus 50 delta A cosine 30, but we need that to be in the x prime direction, so we need to multiply it by another cosine 30, that's a component, plus 25 delta A cos 30, again, need to put that into the x prime direction, and then plus 80 delta A sine 30 times sine 30 plus then this 25 delta A sine 30 cosine 30, which was this one, now needs to go into just a component of that in the delta in the x prime direction, and all of this needs to equal 0, and we get our sigma x prime as negative 4.15 MPa. And now we can do the same thing. Sum forces in the y prime direction. Say this direction is positive. Set everything equal to 0. And we get tau x prime y prime delta A minus 50 delta A cos 30, but it needs to be the component in the y prime direction, minus 25 delta A cos 30 minus 80 delta A sine 30 cos 30 plus 25 delta A sine 30 sine 30 equals 0. And here we're going to solve for, I think I actually forgot a cosine here. Delta A cos 30, delta A sine 30, delta A. Oh, I forgot a cosine here. That's why we're off. Okay, there we go. Now everything should match up. Okay. And now we have tau x prime y prime equals 68.8 MPa. Okay, so now that we have that information, okay. We basically need to draw what's happening on this element. So let me kind of scroll down here. So we have figured out what's happening. Let me scroll up actually. What's happening on the AA plane. And now what we need to do is we need to section it on the BB plane. So we're going to redraw everything for the BB plane and then kind of repeat all of these vector analyses for that plane now. Okay, so I'm going to redraw right here. The same way we did for AA, and we get this delta A sine 30, if this is our 30 degrees, we get a delta A cos 30, and we get a delta A. So everything needs to be multiplied by those components when we put it on here. Okay, let's start by defining our x prime and our y prime. So our x prime here is going to be perpendicular to this plane. And our y prime is going to be parallel. And then here was my original x. And this was my 30 degrees clockwise rotation. And this is my free body diagram, by the way. So let's go ahead and start with our shear. So we have a shear stress here, the shear stress on this plane, shear stress on this plane, and then we have our normal here, our normal here, our normal here. Okay, and now let's define our normal. So we have the 50 delta A sine 30. We have our 25, our 80 cos 30, just multiplied by anything you see here. And then we have here our our sigma x prime, just delta A. And then we have our tau x prime y prime delta A. We have our 25 delta A sine 30, and we have our 25 delta A cosine 30. Okay, same thing that we did before. Summation of forces in the x prime direction are equal to 0. We're going to say this is positive, and we get sigma x prime delta A minus 25 delta A cos 30 sine 30 plus 80 delta A cos 30 in the cosine 30 component minus 25 delta A sine 30 cos 30 minus 50 delta A sine 30 equals 0, and we get sigma x prime is 25.8 MPa. And then we can get sum of forces in the y prime direction the same way. So we can solve for tau x prime y prime delta A plus 25 delta A cos 30 plus 80 delta A in the sine 30 direction. And then lastly, plus 50 delta A sine 30 cos 30 equals 0. And then we get tau x prime y prime equals 68.8 megapascals. Okay, so basically, this is a pretty long analysis. And if we wanted to do this at different angles, it's going to be the whole process repeated again. So we'll kind of leave this for what it is, do a couple more examples, and then we'll move on to using more circle. But this is the idea, this is the theory behind what we're trying to solve for, and this is what happens when we're trying to isolate these planes and figure out what stresses are acting on them. Okay, so general equations of plane stress transformation. So instead of having to go through all that, we can basically kind of go through a procedure and develop equations to use for plane stress transformation, and we'll use these for more circle as well. So this stuff is important. We're going to define our positive x and positive x prime as outward normal from a side of the element as such, so not in the compression way, in the tension way. And theta, this is important as well. Positive is always measured from our positive x to our positive x prime. Okay, so here is the slide that shows you basically how we have come to these equations. So I'm going to go over this, but this is basically what we will be using here, everything in this box, and really primarily these two equations, because you'll kind of start seeing that this sigma y prime is really, it can always be figured out from this sigma x prime depending on what you determine your x prime axis or your x-axis to be. So we'll kind of go over that. But here what we're saying is if this delta A is the area of the element and we section off or isolate this plane, just like we did in the other example, and this is our free body diagram right here, we get all of those exposed forces in terms of theta. If we apply our equations of equilibrium in terms of some arbitrary theta instead of some predefined theta like 30 degrees, which was just for 1, we can get all of these functions of stress as in terms of theta. So all we'd have to do is just plug in the theta and we can directly solve for these values instead of having to do all these crazy calculations for equilibrium every time and keep track of our vectors and everything like that. So you can always just kind of go to these equations and use these instead. Okay, so we're going to try this example, the same example, but instead we're going to use the predefined equations. And before we do, I'm just going to say one of the most important things that you need to make sure you can keep track of is the sign convention. So these formulas were derived based on the sign convention in this slide here, in slide 15. So you don't have the luxury of kind of coming up with your own sign convention or saying that you want to switch things up. You kind of have to just go with what's happening here unless you want to derive your own set of equations. So my tip for you here is make sure you know the sign conventions that the equations were derived for, and make it kind of a monotonous thing when you're doing these problems to really check yourself with the signs, okay? So here, it's the same problem. So the first thing we want to do is we want to figure out what our stresses are in the general x and y directions. So we want to look back to this problem, this kind of sample image here, and we always want to refer to this and say the positive x is in this direction, positive y is here, and the tau xy has to be going towards that top right corner. So we want to come here and we want to ask ourselves here, is sigma x going, let me draw the x and y actually, this might help. Is sigma x, so whatever sigma you see in the x direction, which is 80, is it, why is this, I'll do this, which is the 80. Is it going towards the positive x or is it going away from the positive x? So the answer is away, so here our sigma x is negative 80 MPa. Our sigma y is going towards the y-axis that we've defined as positive, so it's a positive 50 MPa. And our tau xy does not meet towards the corner like in the picture. It goes away. So you see the tail You see the tails in this top right corner, so it's going to be a negative 25 MPa. And this is extremely important that you establish those sign conventions correctly. Okay. So now what we're going to do is I'm going to come back here. I think they call this plane CD, or what do they call this? Okay. So I'm going to actually define some planes here. Let's rotate this. So this is our element. And again, now this here is our, let's say we're going to call this our x prime, because this was our x. So what we're seeing here is we're seeing a rotation of negative 30 degrees. Okay, and if that's my x, then this here has to be my y prime. Okay, and what we've done is we've just rotated this whole block by this 30 degrees, because that's a 30-degree clockwise rotation. Okay, I'm going to call this point here point B, point C, and point D. And we want to look now at this plane CD. Okay, and just some notes before we go. So the positive x prime axis has to be directed outward. From one of the faces. It can't be directed towards it. Okay, so we made it perpendicular to CD. Okay, the y prime has to be directed along the plane of that element, and theta is measured from x to x prime. Okay, so those are some observations that we've made here, and now we can plug into those equations there. So we have sigma x prime. I'll rewrite it here so we can see what we're plugging in everywhere. And now I just get to plug in directly the values I had defined with the signs that come along with them. Okay, so that's our sigma x prime. And now we can plug into our tau x prime y prime. And we have negative sigma x go 2 times negative 30. And here we get negative 68.8 MPa. Okay, now this is for plane CD. So we're going to now look at plane BC. Right, because now our theta value is going to change. So what we'd have here is we'd still have the same rotated element. We would have this as 30 degrees. Okay, and here this now would be our x prime. This now would be our x, and here we'd be rotating counterclockwise 60 degrees, and now our y prime would be in this direction. Okay, so we're just basically checking to see now what this would be. Write that a little nicer for plane BC. Okay, so let's now go ahead and plug in to our sigma x prime direction. we have negative 80 plus 50 over 2 plus negative 80 minus 50 over 2, cosine 2 times 60 plus negative 25 sine 2 times 60, and we get negative 4.15 MPa. And just as a check, we know this has to be the same, but you can do it again for this angle, and you'll see that you should get the same value that you previously got. And we do, we get 68.8 MPa. So what we've done is we've now changed our x and x prime. So this is why I was saying that you don't necessarily need the sigma y equation, but if you wanted, instead of having to do it like this, you could have come here and plugged in the equation for sigma y using theta. So alternatively, I'll write this here. You could have plugged in theta equals negative 30 for the sigma y prime equation, for this equation here. And you'll get the same thing, okay? So it's totally up to you. You can experiment with this problem and see if you're able to get the same answer and how that kind of works out, okay? So let's move on. Principal stresses and maximum in-plane shear stress. So the magnitudes of normal and shear stress depend on the angle. So we've seen that now, that when we rotate this element, the values of our shear and normal stress change. So a lot of times we want to figure out the angle that causes our normal stress to be max and min, and then our shear stress to be max. Okay, so we want to figure out what the angle is that corresponds to these max and min values. And here we have a picture. So this kind of corresponds to the whole topic, not just to where we are now, but basically this is a concrete beam, and we see cracks in this beam. They're very prominent, and these are caused by tension stress. So even though this beam was subject to both internal moment and shear, the cracks here are caused by tension stress, and we can use those stress transformation equations to predict the direction of these cracks. So that's what predicting these angles will tell us, and the principal normal stresses that cause them. So these are super important formulas. These are practical applications that you will be using as an engineer if you go into structural analysis. They're not something that's just totally theoretical, but they're definitely, just looking at this image, you can see how there's a practical application to this. Okay, so in plane principal stresses, so to get the min and max, all we have to do is take the derivative, set the derivative equal to 0, and then find what angle it is that causes the max and min to occur, take that angle and plug it back into our formula. Okay, so we're going to get these two roots if we were to solve for this equation, 1 and 2, and these are both going to be 90 degrees apart, and it tells us basically where the max and min occur, what angle the max and min occur, and then all we have to do is take those and plug them back into our equation, and you'll see here that it says sigma 1 and sigma 2, and we're going to use sigma 1 as the larger value and sigma 2 as the smaller value. Okay, and I kind of put that here, sigma 1 is larger and sigma 2 is smaller. So the set of values, we call them the in-plane principal stresses, and they act on the principal planes of the stress. So they act on the planes that cause these max stresses or max and min stress to occur. And another cool thing is that when we're on the plane where we have these special rotations that cause these max plane stresses, the shear stress along the principal planes is 0. So it's all taken by that normal stress. We have zero shear stress at that point. The max in-plane shear stress here, and that's also why I should come back here. This is also why we don't talk about minimum, because we know the min shear stress is just when we have max normal stress or min normal stress. So we don't have to solve for that as well. That's kind of why. Okay. Where was I? Okay, so for now, for the max in-plane shear stress, so we're talking in this slide, this was normal stress, so this was for normal. Now we're talking about shear stresses. And again, we can come and solve for, take the derivative, set that equal to 0, solve for the theta S, which corresponds to max shear, plug that into our shear formula, and we can solve for our max in-plane shear stress. And then we can also plug this back into our normal stress equation to get an average normal stress that corresponds to the point where we have this max in-plane shear stress. Okay, so here are some important points that you guys can look over when you're solving these problems. And the next example here, I think we'll stop here and I'll complete this next example in the next video. So it looks like we're going to do probably about 3 parts for this topic. Okay, so make sure you review everything here so that you're ready to kind of jump into solving this together. Okay.